Starting today, we're going to look at the actual process of performing radiography inspection. So the first one has to deal with gamma ray radiography. So if we've got in gamma ray radiography, remember we're using a gamma source, which is an element, an unstable element that gives off radiation. Okay, they can be naturally occurring, or what's more often used in industrial radiography, like what we're performing, is they're elements that have been either seeded with extra neutrons, or they've had neutrons knocked off the nucleus of each atom, causing them to become unstable. And so those materials then, we need a way to essentially turn the radiation on or off, right? Because the material itself is always going to be radioactive. There isn't a way to shut it off. So we have to store these things in a shielded container because we don't want that radiation escaping when we're not actually using it. So typically the stored container, here we show a device that's used to an isotope delivery system where there is a lead-lined or a shielded box that is kind of where the isotope lives when we're not actually exposing things to it. And then there's a crank here with a cable. This is like a Teleflex type cable. You've probably seen those, or a push-pull type cable that runs through some kind of a flexible, semi-rigid housing. Okay. And so what happens is, as we turn the crank on here, that cable's going to slide our isotope, our radioisotope, which is in the end of it, it's in a little holder on the end, out this cable and ultimately down to what's called the collimator. And this is another, typically some kind of a lined box. It's very small, but it's got an opening pointing in one direction. Okay, so you can think of it as if it's like a little cube made out of lead where one side is open, so the radiation is really going to only be able to escape in one direction. And that way we can kind of control where that radiation ends up. Okay? So the end of the collimator here can be threaded into different areas or put in certain locations where we're going to do our imaging. So the example you'll see in a minute is we can thread this down. You've all looked on our JT9. When you take the spinner off, you remember being able to see down the spool shaft all the way to the end. You could actually run this down that spool shaft to be able to image things like the combustion chamber or the turbine or areas like that. So in the end, here is to the right is that flexible cable that this is attached to. So that cable on the right there, that's kind of sawtooth looking. That's what's traveling behind here. So that is, oops, not the pointer, pen. That is this thing right here that runs all the way back to our little crank. Okay. And then on the end of it, it's got this little holder that's going to go inside of our source, our isotope delivery system. And I'm going to come back to this video here in just a second, but what can be done here is an example of one of these being used with an engine like I just talked about, where they've removed the spinner cap and we're able to run the source tube down the center of the engine. In this case, they're using a radium-192. And what area, you can see there's film. They've put film kind of around here. What is that? What are we imaging here? What are they looking at? What part of the engine is that? That's the combustion chamber. Okay, so it looks something like this. Here's an engine with the source tube running down the length of it. And you can see in this case the crank is quite a ways away from the little box that would hold the isotope. Okay, so the operator can stand well away where they're not going to be exposed to radiation. And so then what you end up with is an image that looks like this. And here's the combustor, or the combustion liner, as shown. So the radiation source is in the middle here, and then the film is outside, and we're going to we're going to image this combustion liner right here, or can. It looks something right there. And so things you can see on here, a lot of you have looked, we've all looked at the combustion liners during turbine engines class, right? And they had all the little tabs inside of them with the relief slots. You can see all the little tabs and relief slots here. Various holes, cooling holes or air holes, or even that one there right in the middle might be like the igniter hole. Okay. Possibly, I'm not 100% sure, I'm not familiar with what this one's from, but this thing on the bottom on the left is possibly like a flame propagation tube, or it might be another spot where like a fuel nozzle comes in or something along those lines. Okay, so you can see different features. And remember, the film, our film turns black. The dark areas are where high levels of radiation are shown. So you can see the areas that are more dark here, the bands that are more dark, that's where the material is thinner, and then you can see it's lighter in the areas where there's overlapping metal, where you have multiple layers there. Except for between those tabs, you can see everywhere between the tabs, right, there's less material, so you get that darkening taking place. Okay. So now I'm going to go back to that video. And we'll go ahead and watch that real quick. Okay. So that's using a gamma ray source for an X-ray. The other type of source we can use, or sorry, a gamma ray source for radiography. The other type of source we can use is X-ray. And here is, rather than using a radioactive element, we're going to use a type of cathode ray tube, which is the same kind of thing. It's a form of vacuum tube. It's what was in old school televisions. That had the big glass front. It's a different version of one of those. So what we have is a cathode where basically you have a cathode with, there's a low voltage power supply that heats it up, okay, on the left there. And then a high power supply is going to negatively charge the cathode. And then on the right here, there's a anode structure that is positively charged. And so what you'll get is ionized radiation that essentially wants to jump from that cathode to that anode. And as it does, there's a target there. There's a target made out of material that as that ionizing radiation hits that, it's going to cause that target material to give off X-ray radiation, X-rays. And so, again, I've got a video where they kind of explain it a little bit more. I'll show. So we can use that in the same way. So as our energy source, we put our X-ray source on one side of whatever it is we're going to image. We put our film or detector on the opposite side, films being the older, an older system. Nowadays, everything's pretty much using a digital detector hooked up to a computer. And then it goes with this. I'm sure most of you that have been to the dentist, you've experienced this, right? They put the little thing in your mouth. Anyone been? No? Oh. They put the little thing in your mouth. That's the detector. Some may still use film. Anyone's dentist still use film? Yours does? Okay. Most of them, the thing has a little wire coming out of it now. And then they've got that thing they bring down from the ceiling and put next to your cheek. That's the X-ray source. Okay. That's a very small one. That's a very, very low power X-ray. That's why you can get it done every year or so. Whereas the ones we're using for industrial X-ray, they're going to be penetrating much denser materials than your skin and your tissue. And so they're a lot more powerful. And so that's why we have to be a lot more careful with them. Is because they'll be exposing that. So the recording technique, the old film we used to use, used what was called a silver salt in a gelatin, a silver chloride or a silver hydroxide. And so that salt, the film uses, it's a gelatin emulsification, okay, where that silver salt is suspended in it. And silver salts are photo and X-ray reactive. So that means you've all seen probably film, maybe not, maybe I'm dating myself. film that is used in cameras, right, where it changes color, the negatives, the film changes color and then it gets fixed to become a negative. That's salt-based as well. But then that can also be affected by X-ray. And so you'll see when you travel at the airport, for instance, you have to put your bags through X-rays and stuff. There'll actually be a sign on there that warns you if you do have film, especially high-speed film, that you need to have it pulled out for a hand inspection because it'll expose the film just like light will. And so we use that property, in this case, to now image the internal structure of components and parts of airplanes and other objects that we want to look inside of. So these were originally, they came in originally in single dimension. I'll show you what a single dimension image looks like here. It's almost kind of like an ultrasound looking image. And then two-dimensional is probably what most people are familiar with. That's what looks like a picture, right? Where you can see what it looks like if you hold it up. Nowadays, pretty much everything is done in real time. We use a detector, a semiconductor detector, or a grid of detectors that can basically convert, they can measure. It's a bunch of little pixels on the detector, the grid, where each one essentially measures the intensity of the X-ray hitting it. And so a computer then can look at, okay, this pixel's got this intensity, and this one's got a little bit more, and the next one over's got a little bit more, and a little bit more, and then this one has a little less, and a little less, and a little less. And a computer can build an image based on those intensity numbers that are detected by all these different points on a detection grid. Another form you may have heard, many people in the medical side of things have probably heard of computed tomography, okay? But it can be used, CT, or known as CT, or CAT scanning, can also be used in industry as well. And that is, instead of just taking one picture, that's a detector. Again, it's a digital detector. It collects the radiation, but it can do it over time, or it can do it in multiple positions, essentially creating three-dimensional slices. And if you take a 2D image here, and 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 here, and here, and here, and you stack those on top of each other, you can turn that into a three-dimensional image. And so that's what computed tomography is, or CT is. Who's been in a CT scanner, or had like a CT? What is the sound? What does it do when you're in there? Anyone know remember? Maybe. It makes noise. It goes, so you'll be in there. First of all, it makes a lot of noise because there's a lot of cooling going on. But then when they're actually taking the image, you'll hear it go tick, 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 tick. That's it taking a whole bunch of pictures, one after another, one on top of another. And then the computer takes all those images, basically stacks them on top, and creates a 3D model of it. And we can do the same thing with industrial equipment, with stuff here. And so you can either look at those individual slices, or you can build them up to make that 3D model. So what do these look like? So here is an example of a single-dimensional image. Okay, and what it is it's basically telling you how much of an area has a given amount of energy hitting it. Okay, and so at a certain distance, at a given distance, is basically telling you, in this case, 2 inches, you got this real high energy spike. 2 1/4 or so, 3 1/4 or so, right? So you've got energy spikes, and then this is breaking out, the area of 6.5 to 7 there. You can see there's 3 little spikes on the lower right, and then they've kind of zoomed in on that. If that's our area of interest, we can say between that 6.5 and 7 inch area, we've got spikes at just under 6.6, right about 6.9, maybe 6.88, and then just about 6.98, something like that. And so if you know where the area of interest is on your part, you can use something like this. Obviously, this is a very, very old system right here. It's really not used very much anymore. Okay, everything has gone to 2D images, film, and then now everything's gone to 2D and 3D images created by a digital system. And so what does a 2D version look like? Here's a 2-dimensional film, okay? What do you think this is? What material are we looking at here? A composite what? It's a composite honeycomb, okay? You can kind of see the edge. So you have an area where the composite is full thickness. That's kind of below. Here, I'll draw a little line on here. So you got an area of full thickness kind of below. And then you've got an area where they've tapered it down, where the thickness tapers down, the core goes away. And kind of that top part, top left part, doesn't have that honeycomb core anymore. And why do the different honeycombs look different? Why do you have like some like this one that are darker gray compared to this area where they're all lighter gray? What's the difference there? What's that dark gray honeycomb right in the middle of my first circle? Why do you think that one's a little bit darker? Would it be more dense or less dense? There's less material. It's less dense. More radiation's getting through to darken the film. So it's less dense. So it probably contains less resin than the other areas. Okay? Now, why we get that along that edge? Why do you think where that tapers down, it's particularly dense or particularly dark right here? What happens in that area? Yeah, it gets thinner. You have less of the material there. There really isn't a lot of. It's hard to get resin down into that area as you're, say, vacuum bagging. Okay, so you've got a lower density. You know, there's less resin filling in that tapered area. Okay, now, I'm not sure why it's so light on the non-cord area. My guess is they've got a couple extra layers of fiberglass or carbon there, where it's just layers of fabric rather than the core. And so your density increases back at that point again. Okay. Again, I don't know the exact details of this image, but you can kind of speculate what we're looking at here. Here's a 2D real-time X-ray. Many of you have probably seen these if you've flown anywhere, or even train. You know, a lot of train, like you travel by train, sometimes they'll X-ray your luggage. So here we have a luggage. Can anyone tell what's in there? Everything looks like a bomb. I see a laptop, yeah, on the left there. This area on the left is our here. This right here is our laptop. Over here. There's a cooling fan over the CPU. The batteries typically are a little more dense. Those are probably the batteries. Okay. You think that's a radio? Where's the handle and antenna? You think this is the antenna? Yeah, it might be a radio. Yeah, you're right. You know, that's probably the speaker. It's probably the magnet in the speaker that's really dense. Or less. So first of all, this is a reverse image, I'll tell you that. Because look at the belts over here. What's the belt buckle made out of? Metal. The belts are probably made out of like leather or fabric, right? Which one's more dense? Metal. So if it was a standard image, what would it be? Okay, so a standard image, if it was a classic image, the belt buckles would actually be lighter, right? Because they would block more radiation than the belts themselves. So this is an inverse image. So the dense things are dark on here. So the area that I kind of circle, if they say it's a radio, which it probably, now that you mention it, might be, that's probably where like the speaker is that's got the magnet in it, right? That's a real dense magnet. What's that? It looks like a shoe underneath right here. There's like the tip of a shoe. I don't know. Again, it's just it's an image, but it is a reverse image. It is, in this case, erase all, there we go. In this case, more dense is darker versus a standard image, more dense is typically lighter. So to look at how CT works, so we basically take a bunch of these 2D images here or here, and we take slices. And these are almost always done, CT is done with an X-ray system. There's, as far as I'm aware, there's no such thing as a gamma X-ray or a gamma CT scanner. But we have our X-ray tube, and here we've got a test piece, which is like a turbine blade or something, and then a detector array, and they've made a curved array here so that we don't get the what's called parallax, where the radiation by coming out in that cone shape, we want it to travel the same distance to every part of the detector. It's kind of like the curved monitors, so it's all the same distance from your face, I guess. But in this case, what they're going to do is the test piece, the blade, can be moved up and down. So it'll take an image, and then they'll move a little bit, take an image, it'll move a little bit, take an image, move a little bit, take an image, move a little bit. One way you can do it is by moving the test piece. The other way you can do it is by moving the X-ray tube and the detector array. Has anyone's dentist ever done a 3D X-ray for you? Anyone seen one of those? So it's this thing that it doesn't go in your mouth. It has the X-ray sources on one side, detectors on the other. They're on like this thing. You put your head in, you rest your chin on, and all of a sudden it does like this swing around your head. You've had one of those done? Or orthodontist? Yeah, my daughter just had one at her orthodontist, for instance. So orthodontist, some dentists do it. So you put your head in, they tell you to hold your head real still, and in that case now the whole thing swings around your head. And so it can do something like that as well, okay? So you can either move the test piece, you can move the X-ray and the source, you can move both. Some maybe one the test piece can rotate and the X-ray and source can move up and down or back and forth, kind of like what we have right here. So here a part can be rotated, and then the X-ray source and the detector would move together up and down. Okay? And it allows us again to create that 3D image of a part. We can look at these things slice by slice. So here's a CT scan of a turbine blade. You can see it is extremely detailed. We can clearly see every single air passage, gill hole, all that kind of thing. So these would often be used in like an overhaul situation to look for blockages, to make sure there isn't carbon or other buildup inside of these passages, for instance, or for internal cracking between passages or between the surface. Okay? The 3D scan of it looks something like this. Okay, and again, it looks, that 3D model, we can start to actually see the whole thing. And again, looking oftentimes these for things like blockages or cracking internally in these passages that we can't readily do. Or, I mean, you've all done dye penetrant on a turbine blade. How did that work? A turbine blade like this with dye penetrant, what did you see? Or what was that when you did dye penetrant? What kind of limitations were there? They what? You get pooling in the valleys. Did a lot of you get a bunch of indication at like this trailing or leading edge where the holes were? What happened? The dye gets kind of stuck down inside, and then you get a lot of it being drawn back out by the developer. The other thing is, it's oftentimes very difficult to clean these things back out again, too. Right? You wouldn't want to put it in the engine with a bunch of dye dried inside of there. And so there is no cleanup, per se, after you perform CT scan. Really, you don't have to pre-clean very much either, although sometimes you want to. So that's the last of the slides. I'm going to go back. There was a video a couple slides back. I'm going to go ahead and show this to kind of wrap up class.